or the spoons, or the cowbell, or
so you actually
other
are
noisemakers.
complimenting me on a musical
You can
event?
play the harmonica.
Well, think of it. I may have found my instrument at last.
It's about time.
Well, I tell you,
I say you stick with that, and I think we're probably going to do
I may
all right.
have to work on this harmonica thing. Maybe it's my gift.
Yeah, it might be. It might put the kids through college or something. I don't know.
Maybe I should start a gig with the blues band.
There you go.
Maybe I become one of the blues brothers.
You got to get you a little fedora, some sunglasses.
Well, I have sunglasses, but they're kind of more like athletic and triathlete.
I don't know, man. I don't know.
So you don't think?
I don't know. I'm digging the harmonica. That's pretty cool.
The harmonica may be the deal. Okay.
I like it. All right.
Hey, today we're going to talk about the KMT. KMT, what the heck?
KMT, Kinetic Molecular Theory.
That's what it is. Yes,
Wow.
indeed. Well, we're starting a new unit, podcast 5.1. Of course, starts chapter
5.
5.
Yeah. We're going to lump 5 and 6 together here, guys. So.
Yeah. All right. So here is our agenda, or the things that we're going to learn about today. It looks like we're going to go all the way through these 3 objectives. So that's where we're at. And so I guess we should just get at it.
Giddy up, dive in.
Giddy up, giddy ho. All right. So hey, Kinetic.
Kinetic.
What's that mean?
It's
called the kinetic molecular theory. If we kind of break it apart, we can figure out what this word means.
Yeah, kinetic means things are moving.
Kinetic means motion, right?
Yeah.
So kinetic means motion. You ever heard of a guy named by the name of Michael Jordan?
I do remember Michael Jordan.
He's an old guy now.
Yeah.
And he used to play a game. He's pretty good at it, I understand. His name, it was
basketball, I think it was, yeah.
He was a pretty good basketball player. I used to hear that he was kinesthetically gifted.
Yeah.
What was he gifted in, Mr. Sams?
He could move. He could make his body do things that no other person can.
He was gifted in the art of moving or motion. So, a molecular, kind of super easy word. What's that mean?
Having to do with molecules.
So the word molecular comes from molecules. So if you have the kinetic molecular theory, what do you think that really means?
Looks like we're looking at molecules moving.
So let's call it the moving molecule theory. That's easy.
All right.
Or we could just say all molecules
move.
That's it.
Yep.
They're moving.
All.
Are you sure? All?
Well, unless they're at absolute 0, which is 0 Kelvin, they're moving. Even in a solid.
Mr. Sams, we're sitting at a table right now.
We are.
It is a table right here. We're sitting at this table. That's a desk.
Yep.
And it's a solid. It's made of wood. My computer's on top of it.
Yep.
And the table is not moving.
The table is not moving, but the molecules are. They're vibrating.
They're vibrating?
Yep.
That almost sounds weird.
It is kind of weird, but they do.
So the molecules in the table are moving.
Yep.
That's actually correct. You see, folks, what's going on at the molecular level. We think of a molecule as a sphere. These are actually more atoms. There's a line between them, and they're going back and forth. I wish I could show you. They're going ziggity-zaggity back and forth. Think of it like a spring, and they're going back and forth. Okay, so solids move, we say, vibrationally. Back and forth, kind of like a spring between 2 balls. They're constantly in motion. In fact, a way to prove that solids move, everyone to envision a pan that you cook your eggs in. What's the difference between the pan in the cupboard, which is cold, and the pan that is frying the eggs?
The temperature is higher.
So you touch the one, you'll burn your hand. And you touch the other one, and it doesn't hurt. It feels cool to the touch.
Yeah, unless somebody whacks you on the head with it.
That's true. That would hurt. But what do you think what's the difference between them molecularly?
Well, if the temperature is higher, that means the molecules are moving faster.
Yeah. So in the pan that's hot, the molecules are moving fast. Vibrationally, and the cold pan, they're moving slow.
Because it's still a solid pan.
Yeah, it hasn't changed its state.
Right, so they're just vibrating faster.
And what's up with liquids?
They're just kind of cruising around. They're moving. They're still attracted to each other, but they roll around one another. Yeah. Yeah,
they roll around each other. Okay, good. And then gases move. We actually have a sort of more scientific thing instead of roll around each other. They move in.
Gases, they move in a constant random motion.
What's random mean?
Meaning it's unpredictable. It's all over the place. They're just every which way.
So, folks, if I have a, you might want a little sketch of this. If I have a container and it's filled with a gas, we'll indicate them as a circle. They aren't always circles, it's molecular, but they're moving in a particular direction, and another one could be moving in another direction, and another one could be moving another. They're just random, and they hit the side. Sometimes they hit each other, and they bounce. In fact, we have a fancy term is that they collide elastically.
Elastic collision.
Elastic? It's elastic. It's like your waist belt. Okay.
What?
Your waist belt or your waist thing, elastic
you have
pants.
elastic on your pants?
Well, I don't.
It's like old man pants.
Well, I'm not. Well, I am an old man, but you know what I'm saying. Okay. So that said, how fast do they move? Molecules are moving, and we're going to particularly talk about this. This chapter, of course, is about gases. So our focus will be on gases, and so we are going to talk. Ooh, a little typo here. Yep. We are going to talk about how we know they move. Now, some of you have taken physics, and some of you are in physics, and some of you will take physics. You better all take physics. Everybody takes physics. Physics is fun. Physics is fun with a PH. That's right. And so one thing you learn in physics is that there's an equation, and it's printed here, an equation for how fast they move. Actually, you can use how fast they move to determine their kinetic energy. KE stands for kinetic energy. And so if I have this equation, KE equals 1/2 mv squared, if you know their energy, you can actually algebraically solve for their velocity. So how would I do that? Well, I would divide both sides by 0.5 m, right? M stands for mass, by the way, in kilograms. So I can say that v squared equals 2ke over m. Now, why did you put the 2 on the top, Mr. Sams? I have a 0.5.
You're dividing by 0.5. That's the same thing as multiplying by 2.
Yeah, so that's 2ke over m. So how would I solve for v then?
I would take the square root of both sides.
So if I take the square root of v squared, I get v, and that's equal to the square root of 2ke over m.
We should also note that your mass, needs to be in kilograms for this to work.
Yeah, this must be in kilograms.
And the reason for that, if you know what a joule is, when you take physics, you'll figure out what a joule exactly is, but it has to be in kilograms for that to work. And your velocity has to be in meters per second.
That is correct. Okay, so now let's kind of work this out. Let's take an oxygen molecule in this room. So if you look around, everybody, hopefully you're alive, and if you're alive and you're watching this, you are breathing in oxygen. Well, oxygen is the element O2.
Yes.
And O2, of course, has a mass, a molar mass.
Molar mass, yes.
And so we can actually use this cool equation, and the molar mass of oxygen is 32 grams per mole, right?
Yep.
But we, of course, want to convert that to
kilograms.
Kilograms, so I can put grams on the bottom and kilograms on the top. 1 kilogram is 1,000 grams, and that, I believe, is 0.032 kilograms. Did I do that right?
Yep.
And so if I plug this into my equation, I can say V is equal to, and this is a great problem, except Mr. Bergman realized he is not giving you the full equation.
Yeah, we actually just hit pause and had a little conversation here as we left out an equation.
Let's go back. This is very accurate, but we forgot a step. So let me create a blank screen for a moment. We said that velocity is equal to the square root of 2ke over m. But we need to find out what ke is.
Yes.
We had that conversation a minute ago, Mr. Sams, about temperature and how fast the molecules move. Well, there's a relationship where we can take the kinetic energy and relate it to temperature.
Right.
And it's equal to what?
3/2 over RT.
And
or 3/2 times RT, sorry.
So basically we can plug this in right here for kinetic energy. So I can say V is equal to the square root of
3RT over
2 times
3/2
RT over m, which is equal to the square root, we can have our 2's cancel, is 3RT over m. That's
there you go.
Now we should make a quick note about what R is here. Because this is an energy unit, we're going to use the R value that's 8.3145 joules per mole Kelvin.
Yeah.
So jot this down. You've probably memorized from last year.
Yeah, the 0.0821.
0.0821, which we'll use in this chapter. But so there's 2 values you need to kind of
anytime you see joules or energy, you need to use 8.3145.
Perfect.
Got to use it.
All right, so that's our equation. 3RT over m. And so our equation, which I'm back to this stage, is equal to the square root of 3RT over m.
Yep.
Okay, now we know our m from here.
Now that's kilograms per mole, Mr. Bergman.
Yes, but the R has the mole unit in it.
That's
so we are good. That's just going to solve our problem. So we'll say 3 times 8.3145. That's joules per Kelvin mole, I'll put that in big brackets, times the temperature. Now we need to pick a temperature, I guess.
It feels about a balmy 21 Celsius in here.
So if it's 21 degrees Celsius,
that's 294
you add
Kelvin.
273 and you get 294. That's not a divide, it equals. So that's 294, and we're going to divide that by 0.032 kilograms per mole. Now if you kind of do the math, the moles cancel. And actually, I'm not going to get into square root of this, and I'm not going to get into details because joules has interesting. This will come out into so many meters per second. And so what is my value here?
Looking like 478.
478 meters per second. Now, is that fast?
That's pretty fast. That's
Is that really fast?
That's like a mile per second. That's no, not a mile per
Let's
second. That's
figure
like a
that
quarter
out.
mile per second-ish.
How fast? Let's put it in miles per hour for us English people. If I was to do that, I would say there's 3,600 seconds in 1 hour.
Yep.
My seconds would cancel, and I happen to know that there are 1,609 meters in 1 mile. How fast is that in miles per hour?
That is 1,069 miles per hour.
069?
Yeah.
What?
That's what it says.
The oxygen molecule in this room is traveling at 1,000 miles an hour?
It looks like it.
Why aren't you like getting hit by the oxygen molecule that would hurt your body and crush your head?
Well, we are getting hit by the oxygen molecules, but they're really tiny.
How are they so tiny? 32, it said here.
That's kilograms per mole.
Oh, of course, yeah, and a mole's a big number.
Yeah, mole's a huge, ginormous number.
Yeah, so folks, this is kind of weird. The molecules in the room are traveling at 1,000 miles an hour. We just, this may be watched many years later, but we the Houston area, we're not in Houston, but they just got hit by this huge hurricane. And this hurricane had 150 mile per hour winds or something like that.
Yeah.
Basically, wind is air moving, or molecules
Yeah,
moving.
there's a whole bunch of them.
But if you think about it for a moment, they're all moving in a constant random order. You see, and if 10% of them move in one direction, all in one direction, then you can get a 100 mile per hour wind because they're moving on average about 1,000 miles per hour. So it's good that they're moving in constant random motion.
Yeah, they pretty much cancel each other out.
They cancel each other out, but if you get a whole bunch of them all going in the same direction, then that's how you get wind.
And that knocks you over and rips your roof off your house and blows your double wide away.
Yeah, indeed.
Mm.
Actually, I was in a race this weekend, and the guy who beat me, by 2 seconds in fact, was from Houston.
Ah!
He came up because he couldn't be at his house. I almost wish that he didn't come because I would have not lost. It was a funny story. Okay, so it is amazing that they travel at such an amazing speed. That's true of an oxygen molecule or whatever. They move at a very rapid pace. All right. Well, we're back. We had to pause. We had a disruption.
I love the pause button.
Oh, I love the pause button, indeed. Yes, somebody was asking about that today online. Okay, E-fusion.
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 All right.
Is that like when things fuse together?
No.
Oh, it's not
nothing like it. No, E-fusion and diffusion or diffusion or diffusion or something like that. They're sort of kind of related, but here's how this works. E-fusion, if you had a sealed container and you punched a tiny, tiny little hole on the side, we could measure how long it takes for all the gas to escape out the tiny little hole. Okay? So that is that's what we call E-fusion. When gas passes through a tiny little hole.
That sounds almost weird.
Yeah, gas passing through a tiny little hole.
Yes, gas passing through a hole. Okay.
Okay.
That's okay. So yes, but diffusion is how quickly a gas will pass out of a hole. Now this is not a hole. This is a hole that in like a tire.
Yeah.
Like a bicycle tire.
Tiny little hole. Yeah.
Tiny little hole.
Now diffusion is when you have a gas that's released into a large area, and what it's going to do is it's going to go through whatever other gases are in the area. So someone is sitting in the front of the room and squirts some perfume. Those perfume molecules are going to diffuse through the gas molecules in the room. Now, again, remember they're moving at like 1,000 miles an hour ish. Okay. Oh yeah, there's the perfume diffusing through the room. So if I squirt perfume in the front of the room, why doesn't it hit the back of the room at 1,000 miles an hour? Well, it's got all these other little gas molecules that it has to bump through, to randomly move through and bump into and work its way back. So it's kind of like a running back trying to get through a defensive line And they've got to bump through a lot of people to get where it needs to go.
It's kind of think of more like a pinball machine. As
Yeah.
the gas little sphere hits something, it bounces back, and so eventually it's going to make its way back to the back of the room. So again, think of that middle school girl who had just discovered perfume for the first time.
Or high school guys who have the bottle of Axe body spray in their bag.
And eventually it just permeates the room, but it takes time. Even though it is moving at 1,000 miles an hour, it still takes time.
Right, so effusion, we have gas going through a tiny hole, and diffusion, the gas is kind of working its way through the room.
Yes, indeed. Okay,
So don't forget, gas passing through a tiny hole and then working its way through a room, effusion and diffusion.
Okay, how about this Graham's Law? Basically what's that saying? I see it conceptually. Graham's Law is, Mr. Graham was looking at this equation. And actually, we can go back to this equation. In fact, this is related to Graham's Law right here, this equation. Actually, you know, I should say something about this equation that I just solved. I'm going to keep back in this. This is sometimes called the VRMS, or the
root mean squared velocity.
Root mean square velocity. But he basically was saying, what would happen if this mass was big? What would happen to the velocity?
Big mass, the mass is in the denominator, so the velocity is going to get smaller.
And if this number was small,
then the velocity gets bigger.
So when we took it Graham's Law, Graham's is talking about how fast something diffuses or effuses. Basically, massive or more massive molecules travel what?
Slow.
Slow. Now, when we say slow,
relatively speaking,
fast is 1,000 miles an hour. They might be going 600 miles an hour. So don't think of it slow in your world. And then small or less massive, or we can say small, but it's not really the volume, it's the mass.
Yeah.
Less massive.
Travel faster. I think of the elephant and the hummingbird. You got a big old gigantic elephant. Okay, it's just kind of lumbering along, boom, ba-dum, ba-dum. And then a hummingbird has a very, very small mass and just buzzing all over the place. A lot faster. The elephant and the hummingbird. What is that?
That's a hummingbird.
Really?
You didn't think that was a hummingbird?
What's that? Oh, wow.
It's an elephant.
I got the elephant. Sort of, kind of.
That wasn't really a hummingbird?
No, it looks...
Oh, I
don't... Oh, now? Okay, that's better.
There's wings. It was supposed to be wings. That was a stick figure hummingbird.
Let's stick with math and science.
Yeah, I maybe should. My sketching, artistic...
And the harmonica.
Oh, there we go. He needs ears. Okay, Graham's Law equation. Actually, which would be the fastest gas that you could think of?
Hydrogen. That's the least massive.
Because it has a molar mass of just 2 grams per mole. So it would be the most rapid molecule that exists at the same temperature. All right, Graham's Law basically says, it's a comparison. You take the rate of gas 1 divided by the rate of gas 2, and that's equal to the square root of the molar mass of gas 2 over the square root, that says square root, of the molar mass of gas 1. Now I want you to make a quick note here. The 1 is kind of opposite here.
Yep.
This is actually a derivation of that equation, the root mean square velocity. I'm not going to go into the details of how it's done, but this is the equation that you need to use, which we're about to use right now. So let's take a look at this. All right, so we want to calculate the effusion rates of 2 different gases. Actually, these are to find the rates. So we're going to actually use that root mean square velocity. I don't know if we need to do both of these, Mr. Sams, do we? Let's do hydrogen. That's the one we just talked about. So we're going to say VRMS is equal to the square root of 3RT over M. And so this will be the square root of 3 times 8.3145 times, let's say again, 295 Kelvin maybe. That says 295. Sorry, it's hard to just read there. Divided by, and that's going to be, the molar mass of that is 2 grams per mole, so that's going to be 0.002 kilograms per mole. And you come up with a...
That doesn't seem right.
That doesn't seem right.
I must have put something in my calculator. 3 times 8.3145 times 295
divided by
0.002 square root, the answer. There we go. 1918.
1918 meters per second.
That makes more sense.
That's really, really fast, Mr. Sams. I think that's like 2,000.
That's really fast.
More than that.
Hey, can we use the Graham's Law equation with that number and figure out using Graham's law, what the rate of diffusion for the uranium hexafluoride would be? Compare those two gases?
Yes, that's what we could do. I think that might be the next question, but it's not.
It's not on my paper here.
Oh,
so
we'll do it right now.
Yeah, no, I thought that might
So
be
let's
a good
add
idea.
that. And so what we're going to do, so if we know, okay, so if we know that hydrogen travels at 1918 meters per second, what does uranium hexafluoride, that'd be UF6, travel at the same temperature? So we can say the rate of gas 1, let's call hydrogen gas 1. Do I want to do it that way? Yes, I do.
Yes, you do.
And I want to call this gas 2. So I can say actually let me put the equation down. I can say rate 1 over rate 2 is equal to square root of M2 over the square root of M1. Now we know the rate 1 will be 1918. Rate 2 is essentially X. So I can say 1918 over X is equal to square root of gas 2.
352.
Now this adds up to, it'd be 238 plus 6 times 19. Molar mass is 238? No,
352.
352. Square root, though, over the square root of 2, because that's an easy one. And so if you cross multiply, you can say 1918 times the square root of 2 is equal to square root 352 times x. Or, what's 1918 times square root 2? You just solved
I did the whole thing. Sorry. 1918
times 1.4 be 22,000 and some change.
2712.5.
It's 2712 equals, what's the square root of 352?
352, square root 352 is 18.8.
So you divide both sides by 18.8.
2712 divided by 18.8 gives us 144.
So he's traveling at a whopping 144 meters per second, really much, much slower than 1918. So this is just a solve the problem type of a deal. Sometimes they might ask you a question like this. Let's add this question here on this deal here. Sometimes I've seen a question that'll say, how much, so just copy this down, faster is hydrogen than chlorine in terms of rate of diffusion?
Yeah. There we're just going to compare the rates. We're going to get a ratio of the rates.
So what I like to do is I like to call the rate of the slower one a 1.
Yeah.
So the chlorine is the bigger molecule, so it travels slower, and the hydrogen we're going to call x. So we're still going to use the same equation where we're going to say, now we're going to call the chlorine, this will be gas 1, by the way, the hydrogen. Always put the faster one on top. It makes your life easier. And this will be gas 2. And so I'm going to say that x over 1, these are the rates, would be equal to square root of 71, that's chlorine, over the square root of 2. Chlorine is 35.5 molar mass times 2. That's where I got the 71. Of course, hydrogen is 2. So just 71 square root over square root 2 gives you,
divided by square root of 2 gives us 5.95. So about 6.
So hydrogen travels at the same temperature about 6 times faster than does chlorine. So if I was to have a hydrogen spill, gas spill actually, it would travel across the room 6 times faster than would the chlorine.
By the way, chlorine is a colored gas. If you ever see a colored gas, run.
Bad.
They're all poisonous.
All right. Now, let's have a little visit about temperature. A lot of people get temperature all mixed up. What is temperature measuring?
It's the average kinetic energy of a molecule in a sample. So temperature is not really the hotness or the coldness of something. It measures how much energy is in something.
So it's confusing.
Here's our equation.
Kinetic energy equals
3/2 over RT.
3/2.
Or not times RT. Sorry, I keep saying over.
Yeah, we need to do this in a different order, but it works out. We're good. But so if you double the temperature, what happens to the kinetic energy?
Double the temperature, we're going to double the kinetic energy.
Now, what do we mean by double the temperature, though?
It has to double in temperature Kelvin.
Now, very important in all these equations, temperature must always be in Kelvin units. There's very, very few exceptions where it can't be. So when in doubt, convert to Kelvin. And of course, the conversion from Kelvin to Celsius is Celsius plus 273 equals Kelvin.
And it's just Kelvin. It's not degrees Kelvin.
And actually, it's degrees Celsius, but not degrees Kelvin.
Right.
It's actually 273.15 if you want to be exact. Actually, that's not exact even, but closer. Okay. Okay.
All right, what's next?
All right, pressure.
Oh,
We got to talk
pressure.
about pressure. Pressure is these gas molecules. If you got a room filled with gas molecules, they hit the wall.
Yep.
Or they hit you, or they hit me. Ouch!
They hit stuff.
And then they create pressure. So pressure is caused by
Collisions of molecules with walls of containers.
or with the container.
Yeah. So if you got a balloon blown up, the molecules are pushing on the inside of the balloon, holding it out.
Yeah, so the balloon is actually inflated by these molecules hitting the outside. Some, of course, are not hitting it, but those that do are the ones that cause this to occur.
Yeah.
And we use what to measure pressure?
Barometer.
A barometer. Who invented the barometer?
Boricelli.
Mr. Torricelli from Italy.
Torricelli, sorry. What did I say?
Torricelli.
I said Boricelli.
Torricelli. It's Torricelli.
Sorry.
Okay, so we're going to skip a page here, and here is the, for just a moment here, this is a Torricellian barometer. I don't know if I'm pronouncing this right. I fixed it. And this is actually our barometer in our classroom, and I don't know, you can see this here. This right here is a pool of mercury, and this is mercury, the element mercury. Okay, and the way this works is you can then read, it's hard to see, but if you look carefully right, I need a different color it looks like. If I look right in here, there's this column of mercury that goes up and up and up and up and then stops, maybe say right here. Actually, I think it's going to stop right here.
You just kind of read it like a thermometer.
You read it like a thermometer, and it tells you the height of the mercury column. Now, the way that you actually make a barometer, it's actually eminently simple. What you do is you have a container, and it is filled with a liquid. Any liquid would work, although we'll talk about why mercury works the best. All right, and then
I wouldn't recommend getting a pool and puddle of mercury and splashing around in it, by the way.
Yeah, it has some safety issues.
Yeah.
You then
Brain damage.
fill a container up level full with the liquid.
All the way to the top.
All the way to the top. You then take your hand.
Stick your thumb over it.
And you stick your thumb. This is your thumb.
Nice
okay,
thumb.
I know. And then it's attached to a hand. He's got 6 fingers. Okay, and he turns it upside down, and then the pool of mercury, and this is mercury. It then stings upside down, and then it fills. But
it's already full.
It's full, but something intriguing happens.
It falls down.
It falls down, assuming you have a tall enough column.
Yes.
And this height is measured with a ruler. And this ruler measures the height of the column of mercury. And if you live at sea level, it would be at what height on an average day, Mr. Sams?
760
760
millimeters.
millimeters. And what is above this?
Empty space.
This is a vacuum. That's correct. So, but if I was to do this with water, I could do this with water.
Yeah, you'd have to have a really tall column.
Yeah, in fact, you know, folks, what it would have to be is you could do a water barometer, but it would be 30 feet tall.
Yeah.
Or 30 meters. I can't remember which. It's very tall.
Yeah.
So they use mercury. Why do they use mercury?
Mercury is really dense. So you're going to get a lot of mass for a very small volume. So the sheer mass of the mercury is it's being pulled down by gravity. And that's what's creating the space at the top.
So it's actually keeping that column height that it has is the air pressure. The little molecules of air are hitting this, and it's pushing it up into the barometer.
Otherwise, all of it would fall down if there was no atmosphere pushing back down on the mercury.
That's correct. So, and this is true. Now, if you were to go up in elevation, so if you lived in a little town like, say,
Woodland Park, Colorado, perhaps,
at 8,700 feet, what would you discover?
Well, there's not as many molecules pushing down on the atmosphere.
And so you would find...
So that's going to drop even further.
So I think our average pressure on an average day
560, yeah.
is 560 millimeters of mercury. But
570, I think. Yeah,
maybe something like that. So depending on where you live, the pressure is going to be different. If you're a sea level person, it's pretty much right around 760. But if you live up at altitude like we do, it's going to be a smaller number.
Yeah.
All right. Another way to measure pressure is if you're trying to measure pressure of a particular gas, you can actually just measure the height column. This is called a U-tube manometer.
Manometer. Manometer.
There you go. That's a joke. Someone will know. Okay. So what you do is you have a gas that's attached. So this picture maybe is a little bit deceptive. Is that what would happen is you would have this connected over here to some container filled with a gas, and no, I have it reversed.
I think it's backwards, yeah.
Yeah, I did that backwards, folks. Basically, you would have the tube hooked up to this side, and then you would have your gas here, and then you would have, this would be filled with mercury down here, and what you could do is you could just measure the height right here, and this would tell you the pressure of the gas by just measuring it with a ruler, a regular ruler, how many millimeters it is. So it's a very easy little technique. Okay, so that's how you measure pressure. Hey,
there's a question in your homework about that, by the way.
Yes, okay, units of pressure. Hey, we measure in a thing called a millimeter mercury. It's just the height of the column. All right, now a millimeter mercury is often called a torr, after who?
Torricelli.
Mr. Torricelli from Italy, okay. So that's Torricelli, so, but it's the same thing.
Yep.
A torr and a millimeter mercury is the same thing?
Same thing. They're both.
I like to write torr because it's faster.
Yes.
I don't know, I'm stupid or whatever. Okay, and that's equal to one atmosphere. That's a little typo there, looks like. And it's also, we can do it in what they call the SI system, and that's called a kilopascal.
Yes.
And these are just the conversions. So let's do one quick conversion. I don't think this is terribly difficult. So if I have
560 millimeters of mercury.
560 millimeters of mercury.
Our pressure up here today-ish.
What would be the pressure in kilopascals, Mr. Sanders?
Well, we're going to take the 760 millimeters of mercury in the bottom and 101.32 in the top. So 560 times 101.32 divided by 760. And we get 74.7 kilopascals.
And most of the time we're going to convert to atmospheres.
Yep.
So if we did that, you just take 560 torr. Here, I'll do the other version. 760 torr. I'm running a space here. And that'd be 1 ATM. I think it's about 0.7.
It's 0.737.
74, and that'd be atmospheres. So we live at about 25% less oxygen.
Yep.
So so we live in a place where we have a lot less oxygen than probably most of you.
Yeah, we get to go to sea level and feel like we just like run for hundreds of miles.
Pretty cool.
It's kind of nice.
It's pretty nice. Okay, hey, we're going to finish off with a couple of talks about the three big laws. There's Boyle's, Charles, Gay-Lussac's, and Avogadro's laws. So we first of all meet Mr. Boyle. This is Mr. Boyle right here, famous old dude, Robert Boyle. Robert Boyle, and some of you may have even done this experiment. It's a very simple experiment. If I take a gas that's trapped in a syringe, and then I apply pressure to it, as you can see in this picture,
yep.
What happens to the gas?
If we increase the pressure, we decrease the volume. It gets compressed.
If you increase the pressure, then the volume of a gas goes down. So he compared pressure and volume.
Found that they were inversely proportional.
And yeah, because if one goes up and the other goes down, that is said to be inversely proportional. Okay. Now, so Boyle's law is quite simple. He said P1 V1 is equal to P2 V2. And if you draw a graph of this, of pressure versus volume, it is a curve. Asymptotic at the volume there. There's a fancy word, asymptotic.
Yeah.
Okay, or it's an inverse relationship. Kind of like y equals 1 over x. It's not linear at all. That's correct. Okay?
Okay.
That's the simple law. And then we have Charlie. Old Sir Charles. What's his name?
I don't remember.
Anyways, Charles's law. It may have been his last name.
Yeah.
But he said, what happens when you put volume and temperature? So here I have a picture of a a balloon.
Weather balloon.
This is a weather balloon, and here's a guy who's about to release the weather balloon. And so what happens if we were to heat this up?
If you heat it up, the volume gets larger. Those are directly proportional.
So if I have a volume and I look at temperature, is that the higher the volume, or probably let's say the higher the temperature, the higher the volume. So if I were to increase the temperature, so if I put a burner underneath this thing, we put some hot flashy stuff, it's going to cause the balloon to expand.
Hot flashy stuff like fire?
Like fire, yes.
Ah,
hot
okay.
flashy stuff like fire. That's what I meant.
I figured.
Oh, good, yeah. So it would cause it to expand. Or if I put it in the oven, although this probably wouldn't fit in very many ovens, it would definitely cause some issues.
Yeah.
Okay, so we can say... Equation. What is the equation? So we can say V1 over T1 is equal to V2 over T2. And the graph is very simple. Volume and temperature are a straight line. You double the temperature. Now, what important thing to understand...
Temperature must be in Kelvin. Do not do this in Celsius. Because if you're at 0 Celsius, you're going to try to divide by 0.
Have you ever seen...
Can't
like
do that unless
newsman,
you're Chuck Norris.
There you go.
Chuck Norris can divide by 0.
If you are watch the weather guy, and the weather guy says, "Hey, it's 20 degrees out this morning, and boy, it got all the way up to 60 degrees today." The temperature tripled. What's wrong with that statement?
It didn't triple. It's not on an absolute scale. We have to use Kelvin because it's on an absolute scale, meaning there is a 0 is where all molecular motion stops.
So the molecules didn't stop. If we had tripled the temperature, we would all be vaporized.
Toast. Yeah.
More than toast, we would vaporize.
Yes. Vaporized.
Vaporized. All right, we have one more kind of law in this lane, and that is the Lucic Law. The Lucic Law said...
sounds French. Probably French.
I think so, yeah. And he was measuring pressure and temperature. So just think about a moment. Here I have a spray can. And this spray can, if you heat this spray can up, so you do put this in a fire, which if you recall...
on the back it always says, do not put in a fire.
Never put near fire because then it might cause explosion. And you want no explosions. Right. Because if you increase the temperature, what's going to happen?
You're going to really increase the pressure.
So think of that gas molecule, and he's moving at this speed, and all of a sudden, you increase the temperature, he's now going at this speed, and he then will explode, and you'll have shrapnel flying, and you'll get hurt. So if the temperature goes up, then the pressure goes up.
And another thing is, if anybody's ever used a CO2 cartridge for anything, maybe you have a little pellet gun or something with CO2, as the pressure, or if you've played paintball, as the pressure goes down, as you use the CO2 cartridge, you can feel the thing getting cold. So the pressure goes down, the temperature also goes down.
Yeah.
So it's another, if you can change one and the other one changes, or you change the one and the other one.
I had a flat tire just the other day, Mr. Sam's.
On your car or your bike?
On my bicycle.
No, that's no fun.
And it has, I have these CO2 cartridges, and that's how
handy.
I fill my, very quickly. It's like for races. And it's got the little nozzle here, and then I stick it on. And these things actually usually they put a little insulation on the outside because people's hands get frozen.
Oh yeah, you get frostbite.
You can get frostbite because it gets so cold. And here's the equation right here of Mr. Lucic. And if you do pressure versus temperature, it is also a nice straight line. We say it's directly proportional.
Yay!
And we still need to.
Yep. All right. Now we don't really deal with Avogadro's law a whole lot, but that just has to do with moles.
Yeah, let's not worry too much.
Yeah,
about
we're not gonna mess with that one.
Well, we're back. We got interrupted for the 4th time, I think, today. Okay, that's all right though. Combined gas law is if we take all these gas laws together. I'm not going to spin here and derive it for you.
Yeah,
but if
we got P's and V's on the top and the T in the bottom. That's basically smushing the other 3 we just talked about together. You get the combined gas law. And it's because we combine 3 gas laws, hence the name combined gas law.
So the nice thing about this law is that instead of memorizing Boyle's, Charles, and Lucic's law,
learn this one and get rid of the one that doesn't change.
Because if you have, for example, volume is constant. So this number here, V1 and V2, are the same. What's going to happen is the volumes would cancel because they're the same number,
then
5 and 5.
Pressure and temperature and
then you have P1 over T1 equals P2 over T2.
Oh, look at that. It's
and that's the Lucic law. So you get the idea. So this is the combined gas law. Let's do one example here and call it good. So let's say that we have Wilson.
Wilson?
Do you think this is Wilson? You guys ever seen the movie?
Oh, the Tom Hanks one where he has the little volleyball.
Remember the volleyball thing?
Yeah,
Stranded or
something.
Anyways, yeah, Tom Hanks was in this movie and he had this volleyball. Well, this is sort of volleyball. Okay, deal with it with me. Okay, it's a balloon, and we take the balloon to the top of a very high mountain. Now, what do you think the conditions would be? Let's say that Wilson has a volume of, let's say, 1 liter. Okay, what do you think the temperature is to the top of that mountain?
Cold.
Really cold.
0 Celsius, 273 Kelvin.
So it is 0 degrees Celsius, which is 273 Kelvin. And then what do you think the pressure would be at the top of the mountain?
Whoa! Were we talking like Pikes Peak or like higher?
Yeah, that's probably a Pikes Peak type size.
I don't know, what do you think, 0.6 atmospheres?
Yeah, maybe.
Ish, maybe less?
0.55 atmospheres.
Ballpark.
Now we're going to take Wilson to the beach. Look, he's on this nice tropical beach. What do you think the temperature is for Wilson now?
Oh, probably a balmy 72 Fahrenheit. That puts us about, what, 25 Celsius?
Yeah, let's go 30 degrees Celsius.
Okay, so 273 plus 30, yeah, toasty. 303 Kelvin.
303 Kelvin. And I would say that the pressure...
I'm sea level, 1 atmosphere.
I'm thinking 1 atmosphere.
Yeah.
So what do you think we could find out?
Well, we could probably find his new volume at the new conditions.
So, let's do that. All right, so if I use my equation, P1V1 over T1 equals P2V2 over T2.
We're going to try to find
Isn't that like related to
V2.
R2D2? Oh, not something
Maybe.
else. Okay, so we're going to try and solve for V2.
Yeah.
Yeah.
Now, some of you, when you do algebra, you've been taught to plug in the numbers and then solve for your variable. Some of you have been taught to isolate the variable and then plug in the numbers. Either way, you get the same answer. Mr. Bergman's going to plug them in first. It was 273.
I would bet it's probably even colder than that. But
Probably.
We'll deal with it. All right, P2 was 1 atmosphere times V2 over 303 Kelvin. Now let me give you a little shortcut, guys. This is the Bergmanian shortcut on how to solve these problems. Okay, I learned this from my high school chemistry teacher. If you think about it, you're going to cross and multiply, okay? All right, so basically cross and multiply the blues and the pinks. But the ones that contain the variable, which is the pink, you will always divide. And the ones that contain the non-variable, you will multiply. So what you will do is it'll be 0.55 times 1 times 303 divided by 273 divided by 1 equals. And so then you come up with a volume of 0.610 liters. And I just do it all in one step. It's a lot faster. I make less mistakes. I could have solved algebraically for V2, and I could sit and think about what that is, but I just prefer to plug in the numbers and whatever.
That's how I would have done it. I would have rearranged and then plugged it in algebraically. But either way, you're going to get the same answer. Do what's easiest for you.
That's right. So now notice here he went from 1 liter to 0.6 liters. He got hot. Shouldn't he have expanded?
Yeah, but he went down in elevation, which means we have an increase in pressure, so the pressure is going to swish him down to a greater extent than the temperature is.
Yeah, so if you happen to, like when we live here up at altitude, actually we kind of see the reverse. We often, those of us who live in the Woodland Park area, we live up on the top of a mountain, and we typically go down to a smaller town, or a big town actually, to buy groceries. And what happens when we drive up back to home, particularly with things like potato chip bags.
Or pre-bagged salad.
Pre-bagged salad.
Oh man, we've actually had them explode on us.
They will explode as you drive up, because in this case, as you go up, the gas inside of the container expands because of the pressure, not really the temperature, and it oftentimes will blow up. Actually, up here, yogurt is an interesting event.
Oh, does that ever explode on you when you open your yogurt thing?
Yeah, usually whenever, you have to be careful when you open up a yogurt. I like
anything kind of liquidy like that.
That's sealed.
Just kind of
splurts
all over the place.
And so you ought to be careful is that you aim it at, I usually aim it at Mr. Sam's or or whatever.
It's not very nice like that.
Yeah, it just kind of splatters on him instead of on me. So anyways, hey folks, that's the end of podcast 5.1. We've just had the gases. So
Mr. Bergman, since you play the harmonica so well, can you take us out with a little tune?
I think I can.
Wow. I'm so impressed. Bye guys, see you in class.